Okay, in this presentation, I'm going to demonstrate some statistical procedures to use when comparing two groups to determine whether or not they differ significantly from one another and whether or not we can make generalizations about those differences to our population. What's important to point out is that there are two different categories of tests to compare groups. The first type, which is the one that I'm going to focus on in this presentation, are called parametric tests. And what's important at these tests, including in this presentation t-tests, have a couple of assumptions that you need to understand. First of all, they assume that the data, underlying data, the variables that you're looking at, are normally distributed, right? In that sort of nice normal curve. There's some deviations from normality, but we'll talk about that as we're running kind of some of our example tests. But this is an assumption of parametric tests, assuming that our data are distributed normally, and then also very importantly, that the variables you're examining, that you're running your tests on, must use interval or ratio scales. So they must be measured on a continuous scale. In contrast, non-parametric tests, which I'll cover in a different presentation, but I'll give you some examples of those on the next slide. But what's important is that non-parametric tests are distribution-free tests, is what we call them. So they do not require this assumption of normality, nor do they require another assumption called homogeneity of variance, which we'll get into in a little bit later. But essentially, what's important to realize is that for non-parametric tests, you can examine and compare variables or two groups that use ordinal or nominal scales, that is categorical variables, right? So you could look at Likert scales, you could look at, maybe class year differences, that type of thing, those types of variables. But in contrast, parametric tests must use continuous scales. So that's a key difference in these two types of tests. All right, so here are some examples of key parametric and their equivalents of non-parametric tests. In this presentation, I'm going to focus on demonstrating these three types of analyses here in the first column. So one sample t-test, paired sample t-test, and independent sample t-test. Just so you know, though, here's kind of their equivalents on the non-parametric side. But the focus of this presentation here is on comparing two groups using parametric tests, i.e. t-tests. And I'm going to also highlight the importance of referring to the reading associated with this presentation, which explains kind of in more detail how to conduct t-tests, all of these three types of t-tests using SPSS. But I'll demonstrate that as well here in this presentation. All right, so essentially just to remind you, a t-test asks about the probability of getting a difference between sample means when we're drawing samples from an infinitely large population with equal means. So basically, we're trying to determine whether or not there is a significant difference between the mean and some other value in our population. So our first type of t-test is a single sample t-test. So essentially that is comparing a sample against a known value. So for example, a common example of a t-test is comparing a student's test score compared to a population, right? Okay, so this is our example here that we're going to do using our CUIN 841 data set. So GPA, again, we have to look at continuous variables, and GPA is a great example of a continuous variable with t-tests. So we can't do a t-test on, let's say, someone's ranking from 1 to 3 of how satisfied they are with their grades. We need a continuous variable, and GPA is one that we can use. So let's say this is totally made up. We realized, actually in 2020, there was a research study that showed the average GPA of college students in Amhara was 2.67. Again, totally made up. But using our data set, we can look at and do a test to see if the average GPA of Amhara students changed over the last 5 years. So our data set's from 2025. are our students in our current population, does their average GPA still equal 2.67, or is it different, right? So single sample example here, that's basically saying here we have one sample of students from 2025, Amhara students, we have their GPAs, and we want to look at that entire sample and see whether or not the value of their GPAs is the same as what it was 5 years ago, 2.67, or if it's different. And as you'll recall, this is kind of going back to my presentation about inferences. What we can do is we can state this kind of in research hypotheses. So our null hypothesis is that there's no difference, right? That's always our null. No difference between our current students and the students in the past. But then our alternative hypothesis is that we think maybe students' GPAs are different now in our sample compared to the value that it was 5 years ago. So what we want to do is look at SPSS, run a single sample t-test, and see whether or not we can reject this null hypothesis. Okay, here we are in SPSS. And so to run our single sample t-test, we go to Analyze, then we go to Compare Means and Proportions, and then we go to One Sample t-test. And that will pull up this dialog box. Oops, I had already run this earlier, so I'm going to take this out. So what we do here is we find our variable that we want to be analyzing. So that's GPA, right? So we put our test variable over here. And what we need to do is put the value that we want to be testing here. So remember, it was 2.67. We're interested to see whether or not our current students are significantly different or the same as having an average value of 2.67. So you put that in here. One of the things I do want to point out, there's this little options thing here. So the default, and you'll recall from, again, my inferences presentation, all of what we talk about in our conclusions are probabilities, right? Because we can never be 100% certain that there's not some error going on in our analysis. So typically the default kind of benchmark is that we want to be 95%, at least 95% sure that we can reject our null hypothesis. So that's why the default here is 95. Sometimes some academics might do 90, might do 99, but in education, typically the default is 95%, and so we'll keep it at that. But you can also change it here in that sort of options section. So continue. So again, hopefully your screen looks like this, and to run the analysis, we just hit OK. All right, here's our output. Hopefully you can see this. I was trying to figure out how to make my screen bigger, but I can't figure it out. Anyways, okay, so what does this output mean? So first of all, SPSS gives us sort of the basic statistics for our GPA variable. So one of the things I want to point out, just as a reminder, so the standard error of the mean, right, is sort of our error when we're thinking about generalizing our mean to the population. And actually, you can calculate the standard error of the mean if you really wanted to. It's really easy to do. All you do is take the standard deviation and then divide it by the square root of your n. So that will equal the standard error of the mean. So remember, n is the number of cases. We have our sample mean, then we have our sample standard deviation, then we have our standard error of the mean. And all of these statistics are used to come up with sort of the calculation for our one sample t-test results. We could do it by hand, but God bless SPSS, it's doing it for us. All right, so for our t-test, the most important test statistic is our t statistic, which you can see here in the first column. So it's 20.64. So I'm sure you're like, hey, what exactly does that mean? Technically, the t value is the difference between all of our group means divided by the standard error of the difference between group means. But again, SPSS has calculated it for us. And so we just need to say, all right, so if we were doing this by hand to interpret whether or not this t value allows us to reject our null hypothesis, there's actually a table you go to and you look up the degrees of freedom, which is essentially associated with your sample size, right? And then the number of variables that you're using here, since we only use one variable, it's n minus one variable. So our degrees of freedom is 991. And so this entire output tells us how to make a conclusion as to whether or not to reject the null, but just to demonstrate to you how you would use the table. So again, our t statistic is 20.64. So you could go to a table, or you could just Google a table, which is what I did essentially. So here, there's a lot of different, t-value calculators online. So we could say, all right, as you recall, our p-value, or our confidence was 0.05, our confidence interval is 95%. So we want to be 95% certain that we can make a conclusion about our null hypothesis, or we want to say we want less than 5% error. That's what the p-value is, right? So degrees of freedom, we actually, in our data set, our degrees of freedom was 991, right? So that tells us our critical t-value is at least 1.962. And again, there's like actual tables you can look up on this, but the most important thing is coming over here, our t statistic is definitely larger than that critical value of 1 point whatever, right? So that tells us that there's likely, at least we're 95% confident that there's a significant difference between our two sets of measures, or that there's a significant difference between our sample mean and 2.67. So just knowing that, we can say, yes, we can reject the null hypothesis. But let's say, SPSS, again, does us a lot of favors, so you don't even have to go to the internet or a t-table anywhere. You just look at your p-value here, which is the significance column. So that's the probability ranging from 0 to 1 that, assuming the null hypothesis were true, the results in our data set would have occurred by chance. So basically, if it says p is less than 0.05, we can reject the null hypothesis. Clearly here, it's definitely less than 0.05. So we are confident that we can reject the null hypothesis. Also, so I also want to help you interpret this entire output given by SPSS. We can also know that we can reject the null hypothesis by looking over here at the 95% confidence interval of the difference. Since that does not contain 0, we can also know that we can reject the null. So if 0 is in here, between the lower and upper, you can't reject the null hypothesis. But because it's between positive 0.29 and positive 0.35, we can be pretty confident that there's a lot of evidence supporting the alternative hypothesis, which leads us to reject our null that our students' average test score is equal to 2.67. All right, so here we are back to kind of our hypotheses. And again, our results lead us to be able to reject the null. Again, we don't accept it, but we reject it. So how would we write this up in an actual paper or manuscript? An important thing to know is that you cannot just put the SPSS output as a table into your manuscript. You need to look at APA and use their proper formatting. I'm not going to do that here because it's pretty straightforward. Just look at the APA book and put your results into their preferred format. But I do want to show you how to write these results into words in your paper because you'd need to report them as well. So this is what I would potentially say. So a one sample t-test was conducted to determine if the average GPA of Amhara University students in 2025 differed significantly from the 2025 average. So here are the statistics you'd want to report. The student's average GPA in 2025 was, here's our mean and here's our standard deviation. So you report that information. So 2.99. So, just looking at these two, it's like, oh, wow, clearly it's different. But you also need to tell your readers what the t-test said. And so you can say, our analysis indicated a statistically significant difference compared to the 2010 cohort's GPA. And so here's our t, here are our degrees of freedom, right? So you have your t with the little degrees of freedom in case somebody wants to go to, the chart in the book and look this up. And then you give them the t-statistic that was calculated here, as well as the p-value being less than 0.001 again. So that means that our chances of being wrong are less than 99.9%. So that's how you would write up these results in a paper. And again, you'd also want to put your results table in your manuscript as well. It's very important to be as comprehensive and transparent as possible when reporting your results of your analyses. Okay, now we're going to come on to our next type of t-test, which is called an independent sample t-test. So independent samples t-tests are used to compare means of two different groups on the same continuous outcome. So oftentimes you can do either two separate groups. So here I'm going to do a comparison of male students versus female students, or you can do one group measured at two different points in time. So I'm going to give you an example of that next. But here's like an example of independent samples. So males are an independent group than females, but they all are taking classes together and they all have GPAs. So what we do, similar to our previous example, we state our hypotheses here, right? So our null is that there's no difference between males and females. So no, null. And then our alternative hypothesis, we're going to say that males are different from females, that the scores are different. And so can we reject our null hypothesis? Does our data show that there is a significant difference between male and female students on GPA? Let's go to SPSS. All right, here we are. And so just as our single sample t-test, we go up to analyze, compare means and proportions. This time though, we're going to go to independent samples t-test. Our third one is paired samples, but we'll do that next. So independent samples t-test. Let's click on that. Pulls open this dialog box. So our test variable is basically our dependent variable, or the variable we want to be looking at, our variable of interest, which is GPA. So let's move that over to the test variable section. And then, though, in this case, we have to tell SPSS that we want to compare males versus females. So I have my gender variable here, and I click over here, gender, and it pulls up this little question mark. So if we were using the syntax, we could code this more easily, but you can see that the OK box is grayed out. So we have gender here, but you just have to go in to define groups, and we're just going to say, yes, we're going to stick with the way that our variable's coded. Our first group's going to be male, our second group's going to be female. This is useful if maybe you have a variable that has more than two categories and you need to kind of group them into two, because right, a t-test can only do two comparisons, one group versus another group. But anyways, that's getting a little too complicated. So here, yes, we'll just say, yep, we want to use the groups according to the way our data set has them set up. So now we have kind of our syntax is ready, or our menu is ready to go. As with before, we're going to keep the 95% confidence interval, right? That'll give us the results, assuming that P is less than 0.05 or 95% confident that our results can be generalized to the population. So this is what we need, and we'll just hit OK to run our tests. Okay, so once again, our output looks pretty similar to our one sample t-test. First of all, SPSS will give us kind of the descriptive statistics for our analysis. And here, because we're comparing men versus women, it split out male versus female. The number, the n, the mean, the standard deviation, and again, the standard error of the mean, which is calculated by dividing each group's standard deviation by the square root of n. So you could calculate that by hand if you wanted. Moving on now to our actual t-test results. I'll note I should have unchecked this box. We're not going into this last sort of analysis effect sizes. We don't really, that's extra. It's great. The Cohen's d can sometimes be a helpful statistics to report, but for our purposes here, just in terms of understanding the basics of the t-tests, we'll focus just on the descriptives as well as the t-test results themselves. So coming to the t-test results. Okay, so this output is a little bit different, and it includes an additional test because we're comparing two groups. Unlike our previous single sample t-test, we only were comparing our entire sample to a specific test statistic. Here we're comparing the mean of males, 3.0, to the mean of females, 2.98, to see whether or not that difference is significant. And so we have to look first at this Levene's test for equality of variances to know whether or not we should report the output from this first row or the second row. So essentially, this Levene's test is assessing the assumption of homogeneity of variances, and it's also doing, a little hypothesis test where the null hypothesis just for this little test would be that the variance for females is equal to that of males, or the alternative is that the variance of females does not equal that of males. So because this significant this is so high, and the p-value is so high here, as well as the F statistic is so low, that actually means that we can assume that the variances are equal. We're not able to reject the null, right? That the variance of females equals the variance of males. So when this significance is really high, if it's over 0.05, right, and the F statistic is really low, then you want to look at the t-test results in this first row. If, though, this sig here, the p-value was like, let's say 0.001, then you would report the results from the second row. So it's not that your test is completely bonkers, it's just that this Levene's test tells us whether or not we should report the t-test results from the first row or the second one. And when we cannot reject the null, when our significance is high here, then we use this first row. Okay. After you determine which row of output to use based on the Levene's test, you then make your t-test conclusion, right? So looking over here, our t-statistic of 0.534 with degrees of freedom of 978, again, that's related to our sample size and the number of variables in our analysis. Then we look at our significance level. So if we were if we were trying to come to a conclusion as to whether or not the means differ or that male was larger than female, if we can conclude that in the population, men definitely have a higher mean than females on their GPA, that would be our one-sided test, right? Two-sided would just be that they're different. Here's the mean difference between males and females average, right? It's only 0.016. And then we have our standard error here, which helps us to kind of determine whether or not that difference is statistically significant in the population. But if we look here, right, these p-values are not less than 0.05. So we are not able to reject our null hypothesis that there's a difference between male and female GPAs in the population, that this difference is statistically significant. And again, too, you can look at our confidence interval here. There is a 0 here in our confidence interval, right? So our lower value is negative 0.04, our upper value is 0.07, so there's a 0 in there. So that also tells us that we cannot reject our null hypothesis for the t-test, which is that males and females GPAs are significantly different in the population of Amhara students. And it also kind of just makes sense intuitively, right? Looking at this, like this is a very small difference, 0.016, right? We can tell that here from our t-test table, and also we could just calculate it. That's a really small difference. So we would need to have, probably a lot more observations in order to make the conclusion that that difference is statistically significant. But regardless, from this data set here, from the sample size we have, and that's just such a tiny difference of means, our t-test is saying too, that's not statistically significant. You can't even be confident at 95%. This would really be only 70% confident, which statisticians don't use that kind of low level of confidence in terms of being able to reject our null. So in this situation, the GPA between males and female students, we cannot say that there's any statistically significant difference. And again, when you're writing up the results of your analyses, you would create a table that would include those statistics according to APA formatting, and then you would also write up a narrative in your findings section explaining that the two-tailed test you conducted to see if male and female university students' GPAs differed significantly. You would report the average for each group as well as their standard deviation, and then the t-test results, which indicated that there was not a statistically significant difference. Your t, here's your degrees of freedom, your t statistic itself, and then the p-value of your two-tailed test. From the first row, again, the first row of the output, because you couldn't assume homogeneity of variance. You could assume equal variances, that assumption was met by your analysis. So you report the results from the first row of output. Okay, our final type of t-test is called repeated measures or dependent means t-test, because basically the idea is that this is comparing two groups, but it's the same people at different points in time. So you remember the independent sample t-test, our previous one that I just explained, was males versus females. So they're independent, like it's not the same people. But dependent sample t-test is if you're looking at the same group of people over time. For example, if you maybe are doing an experiment, and so you want to look at the average value of the same people before the treatment and then after. That's when you would use a dependent sample t-test. Or if you're just interested to see, here's our example, if there's a difference in students' GPA from the start of the academic semester compared to theirs at the end of the semester. Basically, we want to know if the same people at two different points in time have equivalent means. So our null hypothesis would be that the means are the same from the beginning to the end of our population. And then our alternative that we'd look at is that actually maybe those at the start of the semester might be different from the same people's GPA at the end of the semester. So let's see if SPSS can help us determine what our result is. All right, so our last t-test, we go again into the analyze section, compare means and proportions, and then now we'll go here to paired sample t-tests. And so again, we're comparing two different points in time, our GPA from last semester, which I'm selecting here, and then our GPA from our current semester, which I'm selecting here. And as you can see, so we could run multiple paired t-tests if we wanted in the same analysis, but we're just going to do one comparing our first semester GPA to our second semester GPA. And I'm actually going to suppress the effect size output because we really don't need that actually for what we're learning about today. So, and again, you can always change your level of significance here, but I keep it at the default of 95%, and I recommend you do the same. So we hit OK, and here is our output. All right, so in our first table here, again, we're given the descriptive statistics for our two variables plus the standard error, which again is the sample standard deviation divided by the square root of the sample size. Okay, so GPA last semester, we see that the mean was 2.99. Right now, it went down to 2.85, but is that difference statistically significant? Okay, so just so that you know, we haven't gotten to correlations really yet, but our output gives us the correlation. This is because oftentimes when repeated measures are used, like GPA from last semester to our current semester, they're strongly related to each other because the data are coming from the same people, right? But the correlation table is just given to you as an FYI to give you a more comprehensive understanding of the relationship between these two measures. So we're not going to report that as part of our t-test results, but it's a useful heuristic to see, yeah, of course. It's not like these are totally independent, right? GPA from last semester and current semester are pretty strongly related because it's looking at the same people and their performance over time. But once again, our paired samples t-test output is the most important table to be looking at when we're reporting our results. And how do we interpret this? So As opposed to reporting each measure separately, we're looking at the difference, right, between the first and second semester. So the mean here, this first column, is telling us the difference between first and second semester GPA, which is on average about 0.135. The second column here is telling us the standard deviation of the differences between the means. Third column here is our standard error of the differences between the scores. And this, if we were hand calculating our t-test, that's an important statistic to use if we needed to actually hand calculate, again, our t-statistic. We aren't going to do that because SPSS did it for us, but, you know, it's useful to have. Here's our confidence interval of the difference, right? And then here's our t-statistic. There's no zero, though, as we know, in our confidence interval. So that's telling us something promising, that perhaps our difference here is statistically significant. Then we come here to our t-statistic, which is quite large. And again, we could look it up in our table. But our SPSS is also reporting that for this number of degrees of freedom, this is a statistically significant difference because our p-value is less than 0.001, which says we can say with 99.9% level of confidence that we can reject our null hypothesis and conclude that there is a statistically significant difference between these two means. So likely for the population of Amhara students, their GPA from last semester, we can say that it's statistically significant, the difference, the lower GPA this semester compared to our prior GPA. All right, so coming back here to our hypotheses, we can reject our null hypothesis, right? Because our t-test results indicated that likely there's a statistically significant difference between the two GPAs at the start and at the end. And so if we wanted to write this up in manuscript, we would, similar to our previous examples, explain that we conducted this paired samples t-test to see if the GPAs differed significantly over time, and that we found on average students' GPAs in their first semester were higher than the GPAs at the end of the semester. So here's our means, here's our standard deviations, and that finally those differences are probably not due to chance, and our analysis indicated that this difference was statistically significant. Here's our degrees of freedom, our t-statistic, and p is our probability that we are correct is 99.9% likely. So there's still a chance of error, but we're pretty confident that our results indicate that at the population level, there is a statistically significant difference between time point 1 and time point 2. So that's an overview of our 3 key mean comparisons using parametric tests. Again, the important things with t-tests is that you really need to make sure you're using continuous variables to analyze those types of differences. And in a separate presentation, I'll share sort of the approach to using non-parametric tests should you want to be looking at differences on variables that are measured on a categorical scale, such as ordinal or nominal. All right, so hopefully this was useful, and I look forward to your questions.